eating there, but anyways. Or is everyone now working still on the exercise 1? Right? You're still working on exercise 1? Not anymore. Okay, so we could move on, right? Okay, good. Let's move on. Okay, so today's exercise is about system fundamentals, and basically, okay, first 4 questions are about, well, 3 questions are about linearity, causality, time shift, invariance, and basically then the 4th one is about difference equation, so how well you can follow the signal on the system to derive what is the difference equation. Then, okay, when you have difference equation, what are the system parameters? And then basically calculating the zeros and poles. Then we have a simple system parameters again, zeros and poles of this system, having the same sound sample or similar sound sample as you had earlier. Not exactly the same, it has some other parameters here. Whoa, then I have something funny here. Let me take that one out, compare visually. So that's the system fundamentals thing that we are doing. Okay, and basically I already downloaded some of these pictures what I took from the whiteboard. They're say decent. The lighting is not the best one for this. So first exercise, first point is about linearity of the system, right? And basically the test for linearity is to check if we can use superposition. And for superposition, we need 2 signals. Linearity test. 2 signals, x1, x2, which go into this system. What comes out is the output, and we need 2 variables, and basically random numbers are excellent for testing this kind of systems. Random numbers. Okay, just thinking. So this is basically the f of a times x1 n plus b times x2 n. And the test here is if this function actually is the same as that one. Can you take a and b out, and can you basically take that sum apart of each other? So what we could do is to first, when we are testing a system, we basically formulate it so that system output is given whatever we are giving it as an input. And there, what we could use is a MATLAB functions or octave functions. Okay. Of functions. How many of you have actually already written some MATLAB functions before? Okay, good. 1. So simple function. We can start it directly by editing. So edit, say, my function dot m. MATLAB functions are saved as m functions, m files. .m means MATLAB, either script or function. Does not exist. Do you want to create? Yes, I want to create. There we go. Same thing happens on Octave, I think. And how to say that this is a function? We start it with, say, function definition. And output equals to function name as a function of input. Don't use words input, output. They usually are already reserved for some other use. And then what I usually do, I basically there on the first line after the function there is a description. Simply say function to show how functions are done. And then use it. Say equals my function I, and then you can basically put whatever the description you want to. So the usage of the function. Save it, and then we can test it. I will test it by saying help my function. So it basically gives the first block of those comments, and the help of any M file will give that one as a help. So whatever you want that help to give you back, you will just write it as a first block of the comments. But if you have any comments here, an empty line in between, empty line there, it doesn't do anything for the help. It's only the first block of this commented lines. Okay, and for example, now we could actually do a calculate, for example, let's say first. Wait a minute. I need to think of something here. Okay, calculates simple 2 by input value. So it just multiplies the input by 2, and that we can do simply here. Say output equals input times 2. It could be whatever. So this is just the okay, simple. Right. This is my function. Now I can test if this function is linear. Right. And I use 100 points of random values. So x1 equals rand 1 times 100 there. The same thing for the x2. So we have 2 input vectors which has different random numbers. Why they are different? Well, because the random function gives always different value when you call it. Okay, and I can prove it basically. X1, the first value is that one, and X2 first value is something else. Okay, so fundamentally we have now X1, X2. Then we need a couple of other values. So scalar values A and B. And again, the linearity is basically testing for any values. So I could use a couple of more random values for those. Those are just fine. This is not the perfect test for or basically a mathematics kind of test. This is engineering test. Okay, so those are the test vectors x1 and x2. Then we have these test scalars. Oops. A and B. Oops. A equals one random number. BB equals another random number. There. Now we have enough randomness. Now we basically calculate what is the system output for this signal. So first test that one, calculate the system output for that. Then we will calculate the test signal by running the test signals through the system separately. And then we can basically calculate the difference, root mean square difference. Okay. Y of n. My function AA times x1 plus BB times x2. There, that's the system output for combined inputs. And then we calculate this, the same thing using this formula. And then the comparison. Y test equals AA times my function x1 plus BB times my function x2. That's another one. How to then check if they are different, same or different. We calculate how far those vectors are from each other, which means we calculate the second norm. And since we are doing the engineering test here, zero, or mathematically this should end up being zero then. So these vectors are, should basically, the difference should be a zero vector. But since we are calculating with the computer, it always have some computing inaccuracy, which means that we might actually get a very small non-zero value. Okay, norm. Let's see. Now I need to check the where's the help? Yep. Yeehaw, I got 0. However, I would have been very happy with also some other values. So this is exactly 0 equals system is linear. So, well, quite obvious. It was a system that just multiplies the input with a scalar. We could have actually have a system which looks already nonlinear. Say, system that calculates the square value of the input. Let's calculate that one, y test, and then the norm non-zero. This is not linear system. So that was what the square first one was, the multiplied by the value. Yeah. That was, oops, no, 0, which means non-linear system. And caps lock is on. Okay, so that's a system for the method for testing a system linearity. You just need to have the system function. Make sure that you are feeding in this weighted sum of inputs, and then you check if that is the same as weighted sum of outputs for the same test vectors. If they are very close to 0, how close in principle the machine epsilon, meaning the roughly the how well you can do the calculations in this is 2 to the power of minus 16, or 10 to the power of minus 16. So it's very, very small numbers. So that is the computing accuracy for multiplications or additions in the system. So in linearity test, if you get, say, something to the power of minus 15, it's still, it looks like a linear test, linear to me. Okay, so that is the linearity. The second part, let's see, in exercise 2, causality. Okay. On the causality test, we will do so that we test if there is basically no action before, before input, or reaction before action. That's a reaction before action. So input must change first. This exercise or test you would do basically by generating a causality system, generating input vector, a test vector which starts from 0. Any test vector, and then take also the negative indexes, run it to the system, so calculate the output basically, and then you check if there are any non-zeros in negative side. if there are any non-zeros, then it's not a causal system anywhere before the time 0. Here, the signal can be anything. Anything whatsoever. But on the left-hand side, there shouldn't be anything. Okay. And for that one, I will recommend taking a symmetric indexes on both sides. So we need to know also the the negative time events. Symmetric time window, and then you can, of course, create another function there, and think of how, if I give it n, what kind of signal it should get as an output. On the other hand, let me take a quick look on that one. I think we could do it with the, say, random numbers here also quite well. And basically, how about if we have this kind of system? System that reverses a time. So there's the index of input is reversed. So it flips the time. Test vector x let's take a random samples again with the same number of that we have on index and start it from time step 1. Double and random signal, it looks like this. Oops, not like that, like Yep, random sequence that starts from there. Then basically we need to run the signal so that it looks the quite opposite. So how to reverse the time here? What I could do is to do something like that. This kind of questions you really have to probably do some housekeeping of the indexes by pen and paper. But in my case, I've just basically reversed the order of those values. So from 21 points, which is the size of the XX of that one, with the time step of -1 until index 1. Okay. Using auto indexing again. Whoops. Again, I have typo there. And now the question is, do we have anything on the left-hand side of this picture? stem NNYY. Okay, this is not a causal system. Non-causal. There are plenty of non-zero values on negative index values. However, we can also test that my function. Let's see my function. Just stemming NN my function. Oops. My function with the test vector of x. Okay, there are no non-zero digits on left-hand side. So this system is causal. It's non-linear, but causal. There. By the way, this is not absolute proof. It's engineering proof. It's really an engineering proof. Mathematically, you should go forever and test it with every single vector in the world, and then you can, do it by this method. But mathematicians have already proved a lot of things. So let's do the engineering approach in here. Just in case you have a colleague on a company who is a mathematician and you do a test like that and they say, what are you doing? You said, well, this is just an engineering test. You wouldn't understand. All right, linearity, causality, and the third one was time shift invariance. Right. Oops. Time shift invariance means if a system so basically system behavior remains the same. And what you need is a test vector, another test vector with some fixed time shift, run the same signal and see if actually this one is the same as time delayed function value. Like that. Now the question actually is how we can have a simple system that produces a time delay. I'll just give you one very simple function here. Time delay of k samples can be generated by the following. We take a simple system impulse response or transfer function. Fundamentally, it's just a system with transfer function h of z equals to z to minus k. Well, yeah, that's -1 was basically, if you think of this system delays in block diagram, this is just a different implementation, and if you have several of those, for example, here you have time delay of 2, which is the same as a system with time delay of 1. Actually, those together, right? Okay. And the system parameters for that one would be something. Bk times z2 minus k. K from 0 to n. There. So basically, it is a system which system parameters are zeros except the kth element. So, for example, four-step time delay. I mark it with HH. It's H4. Okay. We have 4 zeros on the beginning. Oops, not 0, 1. So that would be the system parameter vector. And then there's a system implementation in MATLAB. It's called filter. Okay. And we have this nice XX already started from 0. Fundamentally, what we need to take a look is if this time delayed signal after that while would be the same. And there we go. Let's see. So we calculate this first, y of n, and check if that one applies. So y oops. My function, where's my y function? There we go. We have a test vector on xx, right, xx. And that's the time shift invariance test. So that's the original, and then, okay, maybe I should. Okay, and then TSI2 is my function with delayed, which is filter HH1XX. Okay, this you can take as granted now. I will explain later how this filter actually works. So filter is same as LTI system implementation. When you just say what are the system parameters defined by B and A vectors. Okay, whoops, not HH. What did I call it? H4. H4. Okay. So that is the output for when the input is delayed. And now the question is this the same as the delayed output of the original signal? TSID is just filter H41 and That one. Now does it go correctly now? Okay, those should be the two different kind of things. This is my function output for delayed signal, and this one here is the maybe I should actually mark it like this. This is the delayed output of the original signal. Yes, now it should be kind of sort of correct. And now we could calculate the norm of those, the difference. They should come up the same, but I will just use the stem for it. So n y y t s I2 red values, n y y t s I d, and the blue, oops, blue values. Why does it that one to me? Oh, okay, I know why. NA is not for this one. Where's my workspace? There. Where's n is 1 times 21. Okay. Stem doesn't work as I want it. It works as it should. So basically these red and blue are on the top of each other. So they seems to be the same, but the seeing is more than believing, so norm will tell if they are the same. So we can calculate again norm of YTS-I2 minus YTS-ID. That's for some Finnish for you. Okay, so it's 0. So they are seen. So it doesn't matter at what time we take the shift. Would you pause the recording? We will get better lighting for the next session. Okay, so so that was the time shift invariance. So it just means that you need to calculate the value for the shifted output and then shift the output separately for the original one. Check if those are exactly the same. Okay, good. Next part. Determine the difference equation for the following system. Okay, more space. On that exercise, you just follow the signal, mark it, how did the calculus goes, and then you just end up having a formula for the output, which is the difference equation. And that's usually in form of B0 x n plus B1 times x n minus 1 plus and so on. And then my suggestion is that you will actually mark the minus sign and put the feedback terms with appropriate delays and scaling factors on this formula, right, like that. Then reminder of the general form. You have on the left hand side, you have all the indexes from 0 to n of a k times y n minus k equals all the other terms on the right hand side, b k times x n minus k, but in your case you would have that one a some variable times y n, and this variable, when you take a look at the these block diagrams, this is almost always 1 plus some other scaling factor y n minus 1 plus a2 y n minus 2 and so on, depending on how many delays you have on the system. And on the right hand side you should have b0 x n plus b1 x n minus 1 plus b2 x minus 2 and so on, whatever those values are. And the system parameters are these. Okay. If you are using any other values for these vectors than or names as A or B or something like that, make sure that you indicate which one is the scaling factor for the input terms and which are the feedback scaling factors. System parameters basically are vectors A, which is simply here A0, A1, A2, and how many you have those, or B equals B0, B1, B2, however, whatsoever you have there, how many numbers you just happen to have there. So system parameters are those. A parameters, so that's basically a vector. Or B parameters, those are those values, and that's another vector. Since when you take a look at this, X is any input. And then A and B are the system parameters, and now you can calculate the output for those input and the system. Okay. System parameters, which also define the transfer function. Also define the transfer function, and okay. since it also defines the transfer function, we can calculate the zeros and poles. Transfer function h of z was simply that bk z2 minus k, ak z2 minus k, so it has exactly the same values here as the system parameters. Okay, and basically then you can, on MATLAB, you can simply say z-plane, and it calculates those values and shows you the Argand's diagram without the gain, which was b0 divided by a0. Okay, but anyways, I'm asking just some small things here, not much. There, a title, subtitle. Argand's diagram gives, for example, something like that, z1, z2. Those are just complex plane coordinates. And pole 1, pole 2. Same thing here. Just complex numbers on complex plane. All right. So let's try an example. I just say, okay, this would be fun. Say half times x of n plus half times x of n minus 2 minus, okay, why not, minus half times y of n minus 1. So just simple feedback there, and then basically just a couple of values for the forward term and one value for the input. So the general form of the difference equation would be simply something like that. Oops, y. Okay, move everything which has y to the left-hand side, so it also changes the sign. Okay. Then on right-hand side, okay, we have x of n, and we have also half of x of n minus 1, minus 2, but okay, where's the x n minus 1? If I formulate a vector which has just, you know, those half and half, it doesn't have anything information about the x of n minus 1. So each of these vectors, okay, it must be there. So I have half, half, what is that one? Well, it must be 0. Right, so the vector is half, 0, half. For a vector, that's the scaling factor for y of n. So it's 1. Then there's the second term is half plus half. Third term, if you want to put there, it will be 0. Okay. So this is how you get the vector done correctly, let me also put that 0 times y of n minus 1, just, you know, to have keep it, that's not 0 star, but 0 times, okay. Just, nobody said anything about that one. Okay, minus 2, of course. There. Parameters. A, vector, this y of n, multiplier is 1. Then we have half, 0.5. And then we have 0. Right. That's a system parameters for denominator, AK. Then the forward term, we have 0.5, oops, 0.5, 0, 0.5. Okay. Then this is system parameters BK. And this defines the whole system. Transfer function, including the transfer function. So now we can take a look at the zeros and poles. Argand's diagram. There. That's the system. Zeros and poles. Well, those are just locations on complex plane. Nothing spectacular, but we can already say, all the poles are inside of the unit circle, so this is a stable system. Okay. So that's something that should be done for every single new system to check the stability, and you can take it, you know, from the Argand's diagram. It's easy to see immediately there visually where are the poles. For example, we have, say, more than 10 zeros and poles, then it's very hard to see it anywhere else except this Argand's diagram. It's a stable, bounded input produces bounded output, kind of stable. Okay, and I need to take a look. What else did I ask? Calculate zeros and poles, Argand's diagram, determine this, do that. Okay. So if you need the coordinates of the zero pole plot, these are, you know, complex numbers. You can always run the calculate the roots of numerator polynomial poles, well, basically the roots of denominator or divider polynomial. Okay, and some zeros where poles pk, zk. Okay, let's see how to do it. Very simple. Z equals, I said it's roots of the polynomial defined by parameters b. There, those are the numeric values. And yes, plus minus I, and in complex circle or complex plane, okay. Yeah, seeing is believing. Let's see, Yep, looks somewhat okay. So I have roots on -1 and 1. Or poles p equals roots of denominator polynomial a, 0 and -1, -half, sorry. Yes, two poles, one at origin and another one at real axis at -0.5. Those are just, locations on a complex plane. Okay, then I will take a look at this one. Ha, good. All right, and then we have this implementation of the system, linear time invariant system called filter. Now we can test the system. Now we have basically tested the system for stability. We could have done also the linearity test, causality test, that kind of things, as good engineers should. But now we basically can go and start testing or using the system. And the system implementation. That's called filter. And usage of filter. It takes in the filter coefficients B, A, and then the input data X. Okay, we had some sort of X already. It was that funny noisy signal started at point 0 somewhere. We had the test signal. Now we can calculate the output for that test signal for this system, defined by B and A parameters, and XX I had the random values that started on point 0, index 0. Okay, that's the system output for that signal and for those parameters. Now I need to do something here. Figure. Okay. Stem NN. That's our test signal. Okay. So that was the test signal. Let's see if I put it here, then I say, woo, let's close that one. Subplot 2 and 2, stem NN YY test. Okay, that's how this system actually modified the input signal, the lower graph. The upper graph is the original test vector, and that the lower one is a filtered signal. What can we say about the output? Not much. It's hard to tell what actually happened to the signal from this point of view, but it definitely did something for the value. On the exercise, the test system is something like this, which is basically a so-called running average filter. This one does filtering. So where do you actually calculate the average or running average? When you want to reduce the noise. So what you should see on this exercise when you compare the values, you should see the noise variation go down. But that's for you to find out. Okay, I'm a great believer, and I believe that my show for the exercise is done. It's your turn to start working on the exercises. And the deadline for this second exercise is next week, Monday. And exercise 1 deadline is tomorrow. I'll start checking those on Wednesday morning. Okay. Good. That's all. You can stop recording.